Hello, um, welcome to my video here where I'll be solving part one of my transport homework one here. Um, Hopefully the whole video setup is alright. If you're wondering what this black thing is here, it's my phone. Um, I'll be recording what I am writing down here on a piece of paper, as I'm sure the webcam that is like this way somewhere doesn't have the clearest image of what's on my paper. So hopefully this uh, phone cam, give a better image. All right. And so let's move on to what we're actually doing here, what we're solving. And so if we look on the screen here, we are given the velocity profile in the angular direction in the gap between concentric cylinders, where K is the ratio of inner to outer radii. And so what this problem is referencing is something called a Coet Viscometer. That's the sort of general image that we're working with here in terms of geometries. So we got concentric cylinders, as it says in there. And so sort of just to draw it out, this is what we're working with here. And from the top view, that's the inner radii, and this is the outer radii, which I'll denote as big R. And then we're also given, we're also told that K here in this velocity profile is the ratio of the inner to outer radii, and so that's K is equal to Ri to R, so the inner radius to the outer radius. And this K is the ratio. And so, as you can see, this velocity profile is actually one that takes into account the sort of cylindrical nature of the Coet cell. Earlier, which if you aren't in this class, you probably wouldn't recognize it, but earlier we had sort of approximated the two surfaces here, this one and this one, as two flat planes. And we were only able to do that because we assumed that the inner radius was big enough and that the gap between the two surfaces were small enough. But when those two aren't true, the cylindrical nature does play a part in affecting its velocity. So that's what we're actually doing now. We're actually using the cylindrical nature of these two surfaces. We're actually putting that into play now. So continuing on here, we haven't even gotten halfway through the problem. And so omega is the angular frequency in radians per second. And it's actually a function of radial position r there. And it wants us to show that the torque on the inner and outer cylindrical surfaces are equal. And then they also give us the shear rate in cylindrical coordinates, which is down there. Sigma is equal to the radius times the derivative of the velocity profile divided by r. And so let's start hacking away at this problem, right? So they want us to show that the torque on the inner and outer cylindrical surfaces are equal. So what is torque here in this problem? Hopefully I don't move this paper out of view. So I'll be using tau under sub t as my torque variable. Tau here is also used along with the shear stress. I'll be also using tau for shear stress as well, instead with sub s, just to differentiate the two. Well, anyway, moving along, we know that it's the force times the lever arm. And well, what is the lever arm in this case, right? Well, if we look at the coaxial here, we can imagine that there is a shaft sort of going down the center of the quad cell. So down the center here from the top-down view. And the lever arm would be however far we are from that shaft, right? So the force at the top of the shaft when turning, you would have to use more force than you would on the outer, I guess, radius, right? And then even farther for the outer radius. Well, when I first said outer radius, it's that inner radius here, and even farther for the outer radius, right? So our lever arm is the radius then, in that sense. It's that distance from that shaft, which is down the center of the quad cell. So in reality, this L is actually FR. So whatever radial position that we want to put in. And now we're sort of left with how do we sub in for force? How do we find the force? And that's where the velocity profile and the shear rate come in here. And so how are any of this related? Well, this is a viscometer, right? So viscosity, and we had just learned Newton's Newtonian fluids, right? So Newton's law of viscosity. So that's what we'll be applying here to prove that these torques are equal. And so what is Newton's law of viscosity, right? And that would be the shear stress, so tau s, is equal to the viscosity, mu, times the shear rate, which we're given here. And so what is shear stress? So that's the Newton's law part, but we haven't actually found force yet. And force is actually found in shear stress's sort of general definition, in which it's actually force over area. So that's where force comes in. And we'll have to solve the rest here to actually be able to plug it in into our torque equation. And so let's continue on with that. And so we want to find the shear rate here for this equation. So the shear rate, actually, let's write it like this. So we know that it's the velocity profile divided by r. So let's divide the equation that we have right here that were given to us by r. And so v theta divided by r is going to be equal to, since everything's multiplied, we only have to divide, we can sort of, we only have to divide one of those, I guess, units of by r for it to actually, as a count, for it to count for the whole operation. I'm only saying that because compared to earlier when I was doing this problem, I had considered the S of summation, so I had divided every unit in there, by r, and that wouldn't have gotten us to the right answer. Anyway, let's divide by r here. And I'll apply it to the stuff that's in the parentheses. So we get r squared under that big R squared. And then we get minus 1. And then they ask us to find the derivative of this. We got to remember that omega here is a constant. And so is k. K is just the ratio between the inner and outer radius, which are no numbers. So that's also just going to end up being a constant. And so the stuff that we're truly deriving is going to be the thing in the parentheses. So just looking at that, this outer radius is just going to be a number. So that's a constant. We don't have to worry about that. So what we're truly deriving is r1 over r squared minus 1. 1 will go to 0, obviously. 1 over r squared is r to the negative 2. And so just applying basic derivative rules, that becomes negative 2 times r to the negative 3, or negative 2 over r cubed. And so this is what we're looking at here, just to write it down after I've talked about it, over r And lastly, to get the shear rate, we just have to multiply it by r now. So we get this as our shear rate, our general shear rate. Oh my god, I can't write letters. All right. And that's going to be our shear rate. And so we can now plug that back into our Newton's law of viscosity. And now what we have to do is sort of get our area, which is going to be easy. It's just a surface area of a cylinder, right? Move that over and plug it into our torque equation. And so that's what we'll be doing here. So I'll write up here actually. So the area is going to be equal to 2 pi r, whatever radius that we're using, inner or outer, and then times h. All right, and so let's set these up for torque on the inner surface and then torque on the outer surface, and then we'll set them equal to each other just to prove that they are equal. All right, so hopefully I didn't move that too badly. So torque on the inner will be equal to the force. So that's going to be mu times the shear rate, right? So the shear rate in terms of Ri here will be omega k squared. I'm going to bring that 2 out, and the reason I'm not having the negative there is because ultimately that negative is just a directional signage, and so that is something that is ultimately up to the person doing the problem, and so being whatever way is positive, ultimately you just have to denote that at the end. So I'm just going to leave it positive. 1 minus k squared, and then we have r squared over ri squared times the area, so 2 pi ri h, and so that's all of the force portion, right? And now we just have the radius again, so ri. And so we actually have a lot of simplification that we can do. If you can notice right here, r squared over ri squared. Earlier we said that k was the ratio between the inner radius and the outer radius, and this is just the inverse of that. So we can say this is 1 over k squared, right? So these two terms here will cancel, and then ultimately this is equal to mu omega 4 pi h ri squared. Let's just put all that over 1 minus k squared. So let me make sure everything's still here. So that 2 times 2, right? Pi h and then ri squared. So this was ultimately gone, and this is gone. So there's our torque for the inner radius. So now let's find it for the outer surface. So T at R or O, it doesn't really matter at this point. So it's going to be mu, right? The shear rate for the outer radius is going to be omega 2k squared over 1 minus k squared. R squared over big R squared will be 1, so there won't even be that term there. And then it's going to be times the area, times R times H, and then the R from the torque equation, which we have another R. And simplifying that, we'll get mu omega 4 pi, 2 times 2, right? Pi k squared r squared. I forgot the h here. I'll just put h there. And that's all over 1 minus k squared. And so let's set these two equal to see if they are actually truly equal. This sort of serves as a check for the velocity profile and shear rate as well. This will ultimately prove that those are true for a cylinder as well. So mu, so I'll write over here what we're doing. It's equal to CR. So now we're putting the things together. 4 pi h ri squared 1 minus k squared. One minus k squared. All right, so a lot of things can be divided out here. The mu viscosity omega 4 pi h can ultimately be taken out, and the 1 minus k squared can be, I guess, disregarded, but I'll just keep it there for now. It's going to be equal to k squared r squared. And if you look at this, you might think, well, they're not equal, but if we look closely at our numerators here, this k squared r squared is truly the ratio that we had earlier here, that we defined earlier, which is just k times r. Squared it, k squared r squared is equal to ri squared. So truly here, these numerator values are indeed equal, which then proves that the torques at the inner and outer cylindrical surfaces are indeed equal as well. So hopefully everything looked all right here for this first video, and I'll see you.